Our world seems to run on rules, the laws of physics, the steady march of time, the solid line between what is real and what is not. For centuries, we have built our entire understanding of the universe on these foundations. All of our technology, even our most advanced artificial intelligence, must play by these rules. It all works within a system of logic, of cause and effect, of ones and zeros. But what if a new kind of intelligence is coming? One that does not just play by our rules, but operates on a completely different, and frankly, bizarre, set of principles. We are on the edge of a revolution that merges the power of AI with the strange, almost magical world of quantum physics. This is not just about building faster computers. It is about a technology that could challenge some of our deepest assumptions about reality itself. What if the world you see is just one possibility in a sea of countless others? And what if we are about to create an artificial intelligence that can navigate that sea? An AI that reasons using the same counterintuitive rules that govern the universe at the subatomic level. This is not science fiction. This is the emerging field of quantum AI, where researchers are exploring how quantum computers and quantum principles could enhance learning systems, even though most practical applications remain at the experimental stage. The wall we cannot break. For all their incredible power, the computers we use every day have a hard limit. From your phone to the mightiest supercomputers, they all straightforwardly process information. They use bits, which are basically tiny switches. A bit is either a 1 or a 0, on or off. This binary system is the engine of our digital world and has taken us astonishingly far. Still, it encounters serious trouble when problems grow large enough that the number of possible configurations explodes exponentially. Think about designing a new life-saving drug. To do that, you want to know in detail how a molecule will twist and turn when it meets a protein in the body. The number of possible ways it could interact is astronomical, and precisely simulating all of those quantum mechanical possibilities soon becomes infeasible for any realistic classical computer as systems grow larger. The same kind of wall appears when trying to design radically new materials from first principles, crack specific massive optimization problems in finance, or simulate the earliest moments of the universe. These are not just challenging problems. In many cases, they are effectively impossible to solve exactly with current classical hardware. Classical algorithms and AI can still give powerful approximations, but they are often like a genius who can only see in black and white. To go further, we may need a new kind of computer, one that natively handles the probabilistic, many-layered structure of the quantum world. This is where we enter the strange and wonderful world of quantum mechanics. Down at the subatomic level, the comfortable, predictable rules of everyday reality break down. Depending on the interpretation, particles can exist in multiple states simultaneously, become strongly correlated over large distances, and behave as if they live in a cloud of possibilities that only takes on a definite outcome when the system interacts with a measuring device. It is a world that sounds more like a dream than science, and yet its predictions have been tested to extraordinary precision. Quantum computing turns this strangeness into a resource. Instead of classical bits, a quantum computer uses qubits. A classical bit is that on-off switch. A qubit is more like a quantum version of a dimmer switch. In a strict sense, it is a combination of the states 0 and 1 at the same time, with specific amplitudes that determine the probabilities of different outcomes when measured. This property is called superposition. Because a collection of qubits can encode many possibilities in a single quantum state, a quantum computer can, for specific algorithms, process an enormous space of possibilities in ways that are impossible for any classical device. 2 qubits span 4 basis states, 3 span 8. A few hundred qubits define a space of states so vast that it defies direct classical representation. But it gets weirder. Qubits can also be linked together through entanglement. When 2 qubits are entangled, the results of measurements on them are strongly correlated in a way that any classical shared randomness cannot explain. Measuring one gives you information about the other, no matter how far apart they are. This does not enable faster-than-light communication, but it creates a network of quantum correlations that quantum algorithms can exploit to perform certain computations more efficiently than any known classical algorithm. Now imagine giving this kind of computational substrate to artificial intelligence. That is the promise behind quantum AI. It is the marriage of quantum computing's specialized parallelism and its correlation with machine learning's learning and pattern-finding capabilities. The vision is not just to make today's AI faster, but to create new models that process information in ways that more directly mirror the complex, probabilistic structure of the quantum world. Whether quantum AI will routinely outperform classical AI is still an open research question, but early experiments suggest intriguing possibilities. The potential here is staggering. With quantum AI, future systems could start chipping away at some of humanity's biggest challenges. In medicine, for example, instead of relying solely on years of trial and error screening, a quantum-assisted AI might one day help simulate how candidate drug molecules interact with a biological target, narrowing the search for the most promising options. We are not at that point yet, but foundational work is underway. IBM and research partners, for instance, have used small-scale quantum devices to perform quantum chemistry calculations on simple molecules, demonstrating techniques that could scale as hardware improves. In materials science, quantum hardware is already being used experimentally to study simplified models of complex materials, work that may eventually inform the design of better batteries, superconductors, or catalysts. Companies such as D-Wave have used their quantum annealers to simulate specific magnetic systems, demonstrating how specialized quantum devices can serve as laboratories for condensed matter physics. These are early-stage demonstrations rather than everyday tools, but they show the kinds of problems where quantum methods may have an edge. And the relationship runs both ways. AI is already helping us build better quantum computers. Machine learning models can assist with calibrating qubits, optimizing control pulses, and learning error correction strategies, creating a feedback loop in which AI accelerates quantum hardware development, and quantum hardware, in turn, accelerates AI. Recent work shows AI agents autonomously operating superconducting qubit experiments and optimizing quantum gate performance over long runs, hinting at highly automated, self-driving quantum labs. If you find this glimpse into our quantum future as fascinating as it seems, take a second to subscribe and enable notifications. We are exploring technologies that are redefining our world, and you will not want to miss what comes next. Breaking the rules of reality. Beyond solving practical problems, the most mind-bending potential of quantum AI lies in how it confronts us with philosophical questions. Quantum mechanics has always forced us to rethink what reality means. The so-called observer effect indicates that the act of measurement and interaction with a macroscopic apparatus changes the state of a quantum system and shapes the outcomes we observe. Reality at this level looks like a dance between potential and interaction. So, what happens when the observer is an AI system running on quantum hardware and able, in principle, to model a vast landscape of possible states at once? Could a powerful quantum AI help us probe the most fundamental structure of the universe? This idea has inspired some wild but fascinating speculation, including the notion that our universe might behave like a kind of simulation. There is currently no agreed-upon physical test that could decisively prove or disprove such a hypothesis. Still, quantum computers are already being used to explore profound questions in fundamental physics. For example, researchers have used a large-scale D-wave quantum annealer to simulate aspects of false vacuum decay, a theoretical process in which a quantum field tunnels from a metastable state to a lower energy state, with significant implications for the structure of the universe. In these experiments, a controllable quantum system serves as a tiny piece of the cosmos, allowing scientists to study scenarios that would otherwise remain purely mathematical. As quantum hardware grows more capable, such simulations may reveal new insights into high-energy physics and cosmology that are extremely difficult to access with classical tools. As these systems advance, they might uncover principles of physics that are not even on our radar today. When you have an intelligence that can reason using the same quantum rules that underlie the universe, you are not just building a tool to crunch numbers. You are creating something that could reshape how we frame questions about existence itself. At that point, the puzzles are not only about what is possible, but about who or what is doing the asking. The quantum Pandora's box. Of course, this kind of power comes with enormous risks. The same quantum capabilities that could crack challenging scientific problems also threaten much of today's digital security. A sufficiently powerful general-purpose quantum computer could run algorithms that break widely used public key encryption schemes, which is why governments and standards bodies are racing to deploy quantum-resistant cryptography. There is a genuine concern about harvest now, decrypt later attacks, in which adversaries store encrypted data today in the hope of breaking it once suitable quantum machines become available. At the same time, quantum physics is giving us new defensive tools. Researchers are developing quantum-safe cryptographic algorithms and exploring techniques such as quantum key distribution, which leverages quantum mechanics to detect eavesdropping. The global transition to the new standards is already underway, with governments and companies beginning long, multi-year migrations to post-quantum cryptography to ensure today's data remains secure against tomorrow's quantum attacks. The biggest remaining challenge, however, remains technical. Qubits are incredibly fragile. The slightest interaction with their environment, a process known as decoherence, can scramble their quantum state and introduce errors into a calculation. Building large-scale, error-corrected quantum computers that can run long algorithms reliably is one of the most significant engineering projects of this century. Yet progress is steady and impressive. Google's Quantum AI group, for example, has shown that by combining many imperfect physical qubits into higher-level logical qubits using surface code error correction, the logical error rate can actually decrease as the code gets larger, a key signature that scalable, fault-tolerant quantum computing is achievable in principle. Other companies, such as Quera, are pursuing neutral atom quantum processors that can host large, reconfigurable arrays of qubits, and are beginning to explore how to implement error-corrected logical qubits on those platforms. Their work suggests that as more physical qubits are integrated into error-correcting architectures, the quantum states they encode can be made increasingly stable. In industry roadmaps, this has shifted the conversation from whether a truly fault-tolerant quantum computer is possible to when such machines will become practical, even though the exact timelines remain uncertain and depend on overcoming many engineering hurdles. In conclusion, we are standing at the dawn of the quantum age. What began as a strange, abstract theory in physics is rapidly becoming an engineering reality, accelerated by advances in AI and automation. We are building machines that defy everyday intuition, machines that compute in the language of probability, superposition, and entanglement. The fusion of quantum computing and artificial intelligence is more than just another step in computing power. It could mark a fundamental shift in how we relate to the universe. It holds the promise of tackling problems that are effectively out of reach for classical methods and of illuminating questions about matter, energy, and information that we are only beginning to articulate. At the same time, it forces us to grapple with profound questions. What counts as intelligence? What is reality made of at its deepest level? And what is our place in a world where our own creations might soon reason using the same quantum rules that govern the cosmos itself?